everyone, my name is Brianna Johnson, and I focus for my master's practicum on prototyping the UV docking process with machine learning. So this started by looking at a parametric ordinary differential equation. These equations are very popular in mathematics to help simulate some control systems in different engineering applications. But since I'm a data scientist at the Naval Undersea Warfare Center, we decided to focus on AUVs and UUVs for the purpose of this project. So you can see an AUV right here. I'm not going to trick you and ask you to tell me the difference between AUV and UUV. But this was an application of interest for us, specifically looking at the control system when we're trying to automate the process of completing a mission. So this is the standard AUV control system that we have. So the Y of T is the thing that we're most focused on for this research. It is the up and down oscillations that occur when we are doing a mission and launching an AUV in the water. So if you think of a self-driving car, if you tell it to go from point A to point B, all you really care about are the left, right, forward, backward scenarios that might happen. However, when you're in the water, depth plays a huge factor, and things like current, buoyancy, different tides can all influence an AUV and take it off of course. So also in this equation, we have our stabilizer switch S, which can be turned on or off to try and stabilize our vehicle. So a little bit about sea current conditions. I'm not going to give you an oceanography background, but basically we expect our AUV to move horizontally throughout the water. Unfortunately, storms and different weather patterns can make that not possible. This obviously can hinder the performance of any mission, especially if we are trying to dock at a seafloor station and we can't get a stable enough vehicle, we won't be able to get any accurate measurements. So going into how this was actually conducted, so rather than just having a mathematical model and then solving it, we're going to utilize machine learning. We're actually going to use two different machine learning frameworks for this to do a little bit of comparison between Julia's DiffyQ flux and flux packages, as well as Python's TensorFlow's cross. So after training the data set, it's also important for us to be able to predict beyond our time that we initially trained for. Again, when we're in the water with an AUV or UUV, a lot of times our missions are multiple days long. So we want to be able to see how much we can actually train our data and accurately predict it going forward. So before I go into the actual cases that we use, we do have 3 test cases. 2 are with an ODE and 1 was with raw data, but I wanted to put this up here to kind of explain why this is so difficult. So if you have case number 1, y of t equals t squared, it's pretty simple for machine learning to be able to train from this and predict in the future. There's no big shift, there's not a huge change. However, if you look at the right-hand side, if we're only training from -1 to 0, it's not gonna see that switch that we have after y of t equals 1. So we have this case as our first ODE to see if Python or Julia can handle that drastic change in movement, because that's something we would see in the ocean if there was a sudden change in current. So this was our first result. So it is that same equation, like I said. On the left-hand side, we have the results of Python. So it performed quite well. There are a few discrepancies that you can see in the oscillations that it didn't quite match up. But the loss was pretty good. Julia was fairly similar. So this was training on 50% of the data and we had 600 iterations. The only difference was the runtime. So Julia took about 45 seconds per iteration, and that was with 12 iterations. And then Python, on the other hand, we were able to do 30 iterations and it took less than a minute to complete. The reason why we didn't do more with Julia is we wanted to be able to see how quickly we could get good accuracy without having to spend 30 minutes, an hour running it. Moving on to the second equation, we wanted to be a little bit more complicated than the first. We wanted to have a little bit more of a dramatic shift to see again if it could handle it. So we changed, instead of sine of pi t, we did it to sine of 15 pi t, and then we also added e to the cosine equation. Again, Python performed pretty well. Loss was fairly similar. Again, a little bit of a gap with that biggest change in direction, but it ended up working out pretty well. Julia, however, performed phenomenally with this one. As you see that loss, I mean, you have over 99.9% accuracy. But again, the issue was speed time with Julia. This one took about a minute per iteration to run, and Python was done. It took about 4 or 5 seconds per iteration. So after we did this, it was important to use real raw test data. So we did that. We were able to find the data set from Takumi Matsuda and his team of researchers. And this is real raw data from an AUV that is docking at a seafloor station. So as you can see, it's kind of similar to what we tried to do with our ODEs, with the constant changes and the oscillations. You have some large ones, some small ones. So Python, again, TensorFlow Cross was able to do it really well. There weren't many issues. The loss was pretty comparable to what we had seen with the ODEs. On the other hand, Julia struggled a lot in this one. You can see the solid line is the prediction, and then the dots are what was actually happening, and it couldn't really pick up all of the oscillations that were occurring, and its accuracy went down to about 86%. So I'm gonna see if this works. No, I don't think so. So I have a video, but I think this is a PDF, so I don't think it's gonna work. But what it does is it kind of shows how the model's working. Do you have the PowerPoint that I sent you?
Yes.
Okay. Can I switch to that? Maybe it didn't work when I said. So what happens, I promise what happens, is there's a solid line that's the prediction that's all the way throughout, and it starts with one subsection of data. So we'll start from here to here, and then it tries to predict it, and then it will add data. So then it's training from here to here and predicting, and so on and so on. So it's about a minute-long video to show you. And what we really liked about this with Julia is it was doing the shifting data frame so that we could see what was most optimal when we were trying to decide how much we were going to train on and how much we were going to test on. So once it predicted from about here to here, it was pretty accurately able to tell what the rest of the equation was going to be. So this is actually a pretty good standstill of where it is right now, because this is pretty consistent with what the equation ends up looking like. So this helped us be able to tell that doing a 50-50 split was pretty accurate. Anyway, going into some of the research and discussion about this project, we were able to take both TensorFlow Keras and Julia's DippyQ Flux to show that a neural ODE can be used to model the AUV control system. And then we were also able to show, maybe not necessarily so great with Julia, but pretty well with Python, that we can take those same mechanisms to train on raw data found in an autonomous underwater vehicle to predict the movement and specific patterns of one of those vehicles. And I did just want to say, because yes, Julia didn't perform that well on the last test, and it would be possible to get better accuracy if we added more layers or maybe did a little bit more training, more iterations. But again, we were really focused about the runtime, because in practice, when we're doing this with the government, we don't have that much time to be able to train. This was a pretty small data set for what we would traditionally do for a mission. And so we don't want to have to spend hours upon hours training gigabytes of data when Python can handle it much quicker. So just to end, this was a continuation of an undergrad project that I began with Professor Alfa Heryudono. So I do want to give thanks to him and who this was originally funded through as an undergrad, and then being able to continue it from a master's. And then, any questions?
Thanks, Brianna. That was really clear, very interesting. I was just talking to Alfa, wondering about why Julia was so slow. And I'm wondering if you guys have talked to the developers there, I think something that it takes.
So Julia was fun to start working with. I don't know how many people have worked with it, but so they have Julia, I think it's version 1.5, and then Julia Pro. Julia Pro wouldn't work half the time with the packages, and then the regular one worked.
Not very pro.
Yeah, it wasn't. we had some issues. The other thing that I could think of is there was a lot more happening in the background for Julia. So it was producing these images while it was training. And these were essentially, if you want to say GIFs or GIFs, that were also being created at the same time. So part of me wants to think that's attributed because, you know, if you have to render all these images and videos, that's something Python's not really doing.
I'm just thinking you need to let Julia people know, because one of the big ads is Alfa.
Oh yeah, I know.
So for these, like the ODEs, are you predicting, or are you taking the previous data point as an input for every single one, or are you like predicting the like time series?
It's predicting the time series.
Oh wow, okay. That's pretty impressive performance then if you don't have like the previous region.
Yeah.
Have you tested like how far it can go for the performance generation?
Yeah, so we found a 50-50 split was pretty good. I did some numerical tests originally in Julia. They're not on this, but they're on a different PowerPoint. And if we did 25%, it just failed completely. Python could handle a little bit more than 50, but we found 50-50 was pretty much where we could go.
Assuming the data is from ODE, right?
Yes.
More than everything like ODE.
Yeah, this one got a little more complicated, but still worked.
If the data is upfront like that, so the function might be continuous. So that can be a problem. That's our Capstone.
Any other questions? So I guess I have a question.
Yeah.
What happens when you have different, I guess these are ODEs, so there's initial conditions.
Right.
If you change the initial conditions, do you have to retrain anything, or does the model continue to predict the time series pretty well?
I think we tried it once or twice and it still handled it pretty well. I mean, most of these we just kind of started 0, 0 initial condition and didn't go from there. But yeah, we did try it once or twice changing the initial condition, and Python, great. Julia sometimes had issues.
Any other questions? We probably have like another minute or so. Now we can take a